Okay, so we're now going to go on to the second section of this topic, which is electromagnetic waves. So let's remember that electromagnetic waves are transverse waves, so their vibrations are 90 degrees to the direction of travel. They can travel through a vacuum, that means through space, so they don't need any matter for them to travel. Okay, they travel at the speed of light as well, which is 3 times 10 to the power of 8 meters per second, or 300 million meters per second, and that applies to all sections of the EM spectrum. Okay, and again, they travel energy from the source to the observer. Right, we've talked about this, so just remember the angle of incidence is going to be the angle from the incident ray to the normal line, which I've already defined for you. The angle of refraction is going to be the angle, it's going to be the angle between the refracted line with respect to the normal line. Okay, you can use a protractor to measure angles. Okay. And again, your resolution will be to the smallest unit of that protractor. Generally, it's going to be 1 degree. Right, so you need to be able to remember the order of the EM spectrum. So I'm going to go from this way, starting off with radio waves. Remember, so that's the R, microwaves, instructions, infrared, visible light, okay, or visible under X-ray glasses. So under is for ultraviolet, X-rays is for X-rays, glasses is gamma. Okay, so if you remember that, remember my instructions, visible under X-ray glasses, you can remember the order. And if you remember, radio waves have got the longest wavelength, gamma rays have got the shortest wavelength. You're pretty much sorted for your exam, okay? Just bear in mind as well, radio waves have got the lowest frequency, which means they've got the lowest amount of energy. Gamma rays have got the highest frequency, that means they've got the highest amount of energy. Okay? In terms of when we get to the visible spectrum as well, just bear in mind that red light as well has got the longest wavelength, and a violet or blue light has got a shorter wavelength. Okay? We've been through these terms before. Same thing applies to the EM waves as well. They can all do these 4 things, okay? Now, due to the difference in the wavelengths and frequencies, okay, different regions of the EM spectrum will behave differently, okay, depending on the materials they travel through. Okay, so sort of kind of like our atmosphere actually stops some of the regions of the EM spectrum. So all bodies emit infrared radiation. The higher the temperature, the more radiation given out. So if you've got something very, very hot, it means it's going to emit more infrared than something that's at a colder temperature. What does intensity mean? Well, it's the amount of something per second. So if we're going to say, this hot stove is emitting infrared radiation at a high intensity, well, it means it's emitting a high amount of infrared waves per second, okay? Okay, so we're now going to talk about how infrared radiation and their respective wavelengths change according to temperature. So if we look at this graph here, okay, so this curve in particular refers to a lower temperature, okay, whereas this one refers to a higher temperature. Several things to notice, okay, so no radiation is given off below a certain wavelength. So here, okay, below a certain wavelength, we've got literally no radiation. That means this is the cutoff point to infrared radiation, or to the wavelength of infrared radiation. Okay. Other thing to note down: there's a lot of a certain wavelength, which is what we call a peak. Okay, and then less as the wavelength increases. Okay, so after a certain peak, notice that yes, we still get a range of wavelengths. So this is this axis tells us it's the increase of wavelength is going this way. So we do get a range of wavelengths, okay, but we get what we call peaks, okay. So we get a certain amount of wavelengths at particular points, and we call these the high intensity points. So at a lower temperature, okay, if we are just going to compare the amount of wavelengths, yes, we do have a huge range of wavelengths, but at a higher temperature, the intensity of those wavelengths does increase. So we've still got the same, so we still start off with this wavelength, okay, for the higher temperature, and we still go to the this wavelength here, but there's just more of them at the higher temperature. Also, the peak wavelength, okay, is actually lower at a higher temperature to the peak wavelength of the of it at a lower temperature. Okay, so that's important to note down. And if you think about, if I go back to red light being the longest wavelength, so here we've actually got more. We've got a lot more wavelengths in the red region. Okay, so if you imagine red light is this way and blue light is this way. Okay, so essentially as a object heats up, it actually the amount of wavelengths in the blue region actually increases. So if you can imagine this, when you heat up a stove, it starts off being quite red, and then if it gets really hot, it will actually turn white, because we're actually going to get lots and lots of wavelengths adding up. Okay. So if an object radiates the same power as it absorbs, the temperature will stay the same. Okay, so just simple matter of thermal equilibrium. If you've got a certain amount of thermal energy leaving that particular source, as the amount of thermal energy entering it, obviously the overall temperature will stay the same. If an object radiates more power than it absorbs, the temperature will decrease. If an object radiates less power than it absorbs, the temperature will increase. Right, so just bear in mind that the infrared radiation coming from our sun can be reflected by our atmosphere, by the clouds, and the Earth's surface. But it also can be absorbed, because obviously that's how we get the radiation onto the land and the oceans in the first place. Okay, so they can be absorbed by our clouds and by the Earth's surface. Okay, so we're going to now look at which one of these surfaces is best at absorbing thermal radiation. So we've got a non-shiny black surface, a non-shiny white surface, and then a shiny silver surface. They've all got thermometers attached to them. What type of control variables are needed for this experiment? Well, we should have the same starting temperature, that's a good idea. Same type of thickness for the materials, as well as the same distance from the heater to the materials. Also, the same type of thermometers would be a good idea as well. And obviously the one which is best at absorbing thermal radiation will be the one that gets the highest temperature, or reaches the highest temperature after a certain amount of time. Okay, so just make sure for your exam you're comfortable with describing which types of surfaces are best at emitting, absorbing and reflecting infrared radiation. Okay, so please pause the video and make sure you can recite these in an exam. Right, we're now going to talk about which regions of the EM spectrum are dangerous. Remember, as I said, radio waves have got a long wavelength, and gamma radiation has got a short wavelength. Right, so we're going to list some dangers for the EM spectrum now. So microwaves obviously can cause internal heating of body cells. So if you've got a high intensity beam of microwaves, which is obviously what happens in microwave ovens, so obviously that's why you've got to be careful not to put your hand inside them, and obviously there's safety features for you not to do that, of course. However, microwaves can be used in communication with mobile phones, so obviously the intensity of the microwaves is less and less focused in communication with mobile phones. So for now we can say it's actually not that dangerous, but having said that, we haven't got one full generation of humans that have used mobile phones, so we cannot compare data with another generation of humans that have not used mobile phones. So that's one thing to consider. Infrared radiation can cause skin burns. Okay, so obviously that's one thing you need to be aware of. So we've got UV light, which causes damage to your eyes and to your skin, which can lead to cancer. X-rays will also cause mutations, which is damage to your cells not reproducing properly, which will lead to cancer. And gamma rays, of course, are the most energetic, which will cause mutations and cancer and ultimately death if there's too much exposure. Okay, so we're now going to look at some uses for the EM spectrum. So radio waves, obviously, we can get communication, walkie-talkies, that's radio waves, or radio traffic controllers from the ground to aeroplanes, that's using radio waves. Television shows, okay, same thing. If satellite television, the signal goes into space via radio signals and then sent to your television satellite dishes. We've also got communication with microwaves, mobile phones, and obviously cooking in your microwave ovens. Infrared remote controls, as well as cooking from the heat of your oven. Visible light photography allows us humans to see, and other animals as well. UV light security ink, okay, it can be able, also you can detect for counterfeit banknotes. X-rays forming images of your bones and security at airports. Gamma rays can also be used to treat cancer. Of course, yes, it can cause cancer, but if we focus gamma rays, we can actually focus them onto tumors and destroy them. And also gamma rays can be used to sterilize medical equipment, okay? So due to the powerful amount of energy that it's got. Finally, if a metal absorbs some radio waves, it can create an alternating current, and depending on that original signal of those radio waves, so it could be a music track or it could be a message from the pilot, okay, that signal will be converted into an AC signal, which then your computer or your electronic device will then translate it into that original message that the radio wave was sending to the receiver. Opposite is true. If you are now the person sending the message, you will then send an alternating current in your metal, and then the output signal will be the radio waves, which will be sent into space or into the atmosphere, okay, for the receiver to detect. And lastly, when an electron absorbs electromagnetic radiation, so it could be visible light, could be infrared, okay, but some form of EM radiation, that electron will move to a higher energy level, okay, and when that electron falls back down, okay, and we call this excitation when it moves to the high energy level, but when it actually falls back down, it will emit energy of that same type of wavelength as the original EM radiation that caused it to rise. And that ends our video on P5.